Good afternoon, and welcome to another installment in the seminar series on advanced transportation technologies. We are very fortunate to have with us today Professor Imran Hayee from the Duluth campus of the University of Minnesota. And I'm going to just give you a little intro about Professor Hayee before he begins his talk, and the title is right there in front of you. Professor Hayee basically received his PhD from the University of Southern California in 1998, and then spent 6 years in private industry. He worked with Bell Labs for a number of years, and then a startup. The Bell Labs operation became the AT&T Submarine Systems. His background originally was in transoceanic optical fiber telecommunications. That's where he did most of his work way back when. He has 13 patents based on that work back then. And then he joined the University of Minnesota in 2004 and has been with the Duluth campus since then. And so he's been working in wireless communications, fiber optic communications, and recently, as I understand it, with some medical device technology. So without further ado, Professor Hayee. And please remember that because this is broadcast wirelessly over the internet, if you have questions, we prefer that you talk into the microphone so people off campus can hear the question. So anyway, with that introduction.
Thank you very much for a nice and kind introduction. And thank you very much for coming here to listen to this seminar. I'm honored, although I had to drive for 2.5 hours, but this went away to see the room is fully packed. And plus, this is also being broadcast online, so maybe a few people will be listening to this as well. As you know that the topic is development of a traffic information acquisition and dissemination system for work zone environment. This work which I'll be presenting actually is a result of last couple of years of research which we are doing in Duluth campus along with a few of my students. So this is a DSRC based system. I'll talk more about it. But before I start, the motivation originally started with the DSRC spread, that DSRC is dedicated short range communication. Most of you are familiar with that. And I would say a small minority of you is also familiar with this work, either fully or piecemeal. So I apologize if nothing is new for them, but for most of you, if you are not familiar with this particular work, this will be new to you. So with the DSRC, this is the vision which is not going to happen in near future, a long time from now. But safety, mobility, and efficiency, you can see this is the goal of intelligent transportation systems. And DSRC is considered one technology which can make this happen. So considering that, I just want to give you the broad outline of my talk. First, I'll talk about just brief introduction of DSRC technology. I won't take that long in that because most of you might be already very familiar with that. And then I'll talk about this development of user interface, which this project actually initiated this work in Duluth. So I'll just mention, I'll take a few minutes to talk about that. And there is a reason, because this was not only about user interface development. Because of this field demonstration, this was directly related to or became the base of ongoing work. So I'll mention about that as well. And then I'll mention about V2I based message alert system, means vehicle to infrastructure, and talk about work zone environment, then system architecture overview, system design, and then the field demonstration. This is what we did last year. And then there were some limitations in V2I based systems, so we tried to overcome those limitations with V2V based system. It's basically V2I based system with V2V assistance. So we also did the demonstration just recently, this past summer. So I'll mention about that as well. And before I summarize the work, I'll conclude the talk. So The first part, I'll just take a few minutes to talk about some of the aspects of DSRC technology. DSRC technology is a dedicated spectrum which is 75 megahertz wide, around 5.9 gigahertz. There are, these are standardized channels which you can use any of these channels to do the operation, and then the channels could be 10 or 20 megahertz long, and 10 megahertz channel means you can transmit 27 megabit per second, and 20 megahertz channel means you can transmit 54 megabit per second. And normally you can operate two channels at the same time, control channel and the service channel, or the application channel. And why DSRC as compared to Wi-Fi? Wi-Fi is a technology, Wi-Fi routers almost everybody has at their homes, and also within university there's a big network of that. Or WiMAX, the bigger Wi-Fi is WiMAX. But I think DSRC has something unique as compared to that. It is fast network acquisition, low latency, high reliability, priority for safety applications, interoperability, and security and privacy. These are, some of these things you can have in Wi-Fi as well, but really low latency and high reliability and fast network acquisition. These are the key elements which DSRC you can compete with. Wi-Fi can compete with that, and it's not about really DSRC. Most of you probably familiar with that. It's not about this particular spectrum around 5.9 gigahertz. It could be the spectrum you can really take anywhere on that electromagnetic chart, but basically it is the speed and it's the dedicated part of it which is more important. So really DSRC advantage, this is kind of redundant, but low latency up to 1 kilometer. This is specifically the DSRC devices which have been developed, 1 kilometer wireless coverage range. Although the devices which we have been using for our demonstration, we couldn't get 1 kilometer wireless coverage, and there were a couple of reasons which I'll mention later on. We were only able to get half of this. Detect vehicle speeds up to up even 100 miles per hour. It works. Built-in security. This has standards have been developed. You're familiar with that for the DSRC security. Weather doesn't really affect that. So multipath interference it's intolerant to that, are tolerant to that. So, and also standardized interoperability, just like Wi-Fi has been standardized. The DSRC is pretty much standardized right now. So, and multi-channel operation. And then V2I means vehicle to infrastructure. Vehicle to infrastructure means that you have to have at key locations at least some infrastructure devices, some DSRC devices, roadside units, which can talk to the vehicles which already have or will have DSRC units. So some of these applications are emergency warning system, approaching emergency vehicle warning, electronic toll. You could do this electronic toll. You can do weather and road condition warning, and curve speed warning, do not pass warnings, and the travel time, for example, the work zone warning, which we have developed the system, that also falls under that. And the V2V applications where vehicles can talk to each other using DSRC. There are many other applications. Can be emergency warning system for vehicles. This also V2I, but V2V as well. Cooperative adaptive cruise control, cooperative forward collision warning, intersection collision avoidance, lane merge assistance, and left turn assistance, and so on. So there's a long list. You can Google it and you can find many applications, and many people are really working towards that. And not though, I would say at this point, not many practical systems have been developed. Theoretically, a lot of analysis have been done using DSRC. A lot of these things actually people have done using some cell phones. For example, Berkeley PATH project they have done. Michigan DOT has done a lot of these works, but not necessarily, not all these things have been demonstrating using DSRC technology yet. And this is from one of the white paper from US DOT, last year's white paper. This was the analysis which was done. If DSRC is out there, it's to deploy DSRC, this is a chicken and egg kind of thing. After this, I'll talk about that a little bit. But that analysis said that 82% of all crashes by unimpaired drivers could be avoided using V2V technology. And V2, actually, I think it's my typo. This is probably V2I technology. And V2V were placed, then 16% of crashes could also be potentially be addressed by V2I technology. Okay, sorry, this is okay, this is V2V, and then in addition to that, if V2V were present, additional 16%. So basically you can see this analysis, this is in this website, you can find out that this has a lot of potential in terms of just the analysis part. But I think the problem is that how to deploy that? Who will spend money? That first, of course, the emphasis was that you can build infrastructure that is cost prohibitive. Then how to find out, how to convince auto manufacturers to put the units in their cars. I think the purpose of sharing this with you is that the research work which we have been doing in Duluth, that basically tries to facilitate some of these decisions which need to be made so that the deployment can be done. The work which we are doing is kind of an application which shows that if this is deployed, this is available, this can be useful. So this is the direction of the work which we have been trying to do. And having said that, I'd like to move on to now directly the research work which we have been doing. And the first part is the development of user interface. This is not directly related to this research work, which really is the base, which is the reason that I'm here to describe. But I would like to mention about this, especially the field demonstration part, and you'll be able to understand why I am describing this work in the context of this. The user interface part is this, that these are my two students. He has graduated, and he is defending actually next month in November. He's all ready. These are the DSRC units. In the beginning, when we started doing work, we did not have these units. And actually, it's about 3 years ago, and we did not know that where we will be able to get these boxes from, the DSRC boxes. And our idea was that everybody has Bluetooth these days in their cell phones. So what about if the DSRC devices are available and this becomes common? Then what about how to interface it with the driver? The new vehicles which will have built-in DSRC units, they will have, most probably, once this is decided, they will have the nice navigational, just like GPS navigation user interface, that kind of user interface. But the cell phone, at that time, we thought that the vehicles which are out there, which don't have the built-in DSRC, they will probably purchase these DSRC devices and they will use their cell phone to interface, which is not a good idea. I don't really think this is practical. This is not going to happen, because cell phone is too distracting. But this is what I'm telling you is this is at that time our thinking was. And what we tried to do was we developed this hardware unit which could interface with the DSRC unit as well as with the cell phone seamlessly, so that it can become the user interface for the person who is carrying the DSRC box, just the DSRC box. But right now the DSRC box has a built-in Bluetooth interface as well. So all what we had to do was write the software. We did not technically had to develop the hardware. And this is where things go. You know, our central station for the demonstration part, central station was the computer-controlled DSRC unit. It communicated to the DSRC unit inside the car, and that communicated to this hardware, which basically sent the messages, safety or travel time or convenience messages to the cell phone, which was Bluetooth enabled. The infrastructure was, this is just the Linux-based platform, and that's what is used to interface with the Sawari unit. Ultimately, we were able to get the Sawari units. That is what we have been using since then, even for the demonstrations which we have done recently. These are the Sawari units, and I think some of you, I know in this campus, you are using Arada units also. And we just came to know about them recently, and we are also planning to buy some. And I think they might turn out to be a good alternative for the Sawari network units. in terms of cost effectiveness also. I think they're quite cheap as compared to Savari network units. They are 500 megahertz AMD processor, 256 MB RAM, and compact flash is this, and they are Linux platform, and that's really, I think the Arada units also kind of match with these specs. This is what we developed, and you can see this is really the Rabbit core module, and this is the Bluetooth module. So this is our microcontroller kind of thing which controls this, and it also interfaces with the Savari network unit, and actually does all the work. In addition to this, what we needed was that to make the cell phones work, we needed to develop the software for the cell phones also. And we chose two platforms for the cell phones. One was the Java platform, GSR82, and at that time smartphones were well, iPhone was out, Android was not, but they were not as popular as you have seen just in the last 3-4 years. So we chose this Java platform, which most of the cell phones had Java platform. So we wanted to write the software so that many people could use that software. And similarly, for the smartphone at that time, we chose the Windows Mobile platform. So we wanted to make sure that we can show the versatile. Windows Mobile had some problems. They did not really allow Java platform GSR82 to be used as such. So this is why I think we tried to develop those softwares for these two platforms. And basically, I wanted to talk about this for this reason. Once we did that, we tried to do the demo at that time. Although for the user interface, demo was not really needed, but the demo was needed to evaluate also the DSRC units which we had. So what we did was we had the three scenarios. One was we had the elevated fixed RSU and then mobile OBU. And the second scenario was the fixed RSU and mobile OBU, but both of them at the same level. You know, the line of sight could have been the problem. We put the RSU on the top of the roof of the car, and then OBU was just passing by. And then the third one, we try to make both DSRC units, try to put both DSRC units inside the cars so that we could check V2V kind of scenario. So for these three scenarios, what I'll show you is, you can see that this is the elevated fixed RSU and mobile OBU. The range which we were able to get was about 1,600 feet, not that much. Here you can see 2,000 feet, and this is in the rural area. This is the urban area, this is the rural area. We were able to get here about 3,000 feet, which is about 1 kilometer. And that's the urban area. And I wouldn't say this is the 3,000 kilometer totally, because our RSU was here. So technically half a kilometer we were able to get in that. So this is the limitation. We were able to evaluate our units which we had. And the reason was that they had omnidirectional antennas. You can have the unidirectional antennas, but not for the V2V application. They are very useful to increase the range. And some, you can use some power amplifiers to increase the range also. But basically, the omnidirectional antennas and the maximum power which we had in our Savari units, we were able to get only half a kilometer of range. This is the V2V scenario. V2V scenario, of course, if this is road has troughs and crests, the hilly area, if it can block the line of sight, this is a problem. But the work which we have done now recently, where V2V assistance for the work zone travel time acquisition system, we will see that this line of sight is not as critical, because the way it works is that any vehicle which is in line of sight to the other vehicle can actually carry the message forward. I'll talk about that in a little bit later. And now I think after just introduction of this, I'll talk about now the basic system which we developed last year and demonstrated it, and then added the V2V assistance part to this. I'll talk about now this. So first I'll mention a little bit about work zone environment, and then talk about this system architecture. So work zone environment, you're all familiar with that. I don't really have to spend time on this. But I would like to say that this is what we have seen, right? I know that there are some products available, Bluetooth using Bluetooth technology to acquire the travel time. I'm not fully familiar with that, but this work is using the DSRC based technology to acquire the travel time. But right now, of course, this is the kind of thing, 40-minute to end of work zone, gives the drivers some satisfaction because they know what is happening, so they can actually wait. So I think the idea of acquiring travel time and communicating to the drivers really stems from the fact that at least we should inform them, and so that they can, you know, stay calm, or if they find an alternative route, they can arrange for that. So I think this is there's human factors involved in it. The current approach of this is, in addition to that Bluetooth, I don't know whether the Bluetooth-based devices are being used or not, but you know, the traditional method is the loop detectors, and you can actually calculate or estimate the travel time to some extent, and then you can communicate to the driver. So this is the approach. But with the DSRC technology, by the way, many other things are possible. The advantage of DSRC is that this is just one application which we are doing. Many things can happen in parallel. Just those examples which I listed earlier, V2I based and V2V based, many things can happen in parallel. And this can happen as well, that we can estimate very easily travel time as well as the start of the congestion location. This is important as well. If the driver knows who is approaching to the congestion, and so how far is the start of congestion, the queue where the congestion starts. So that can also be helpful to the driver. So these are the two parameters which we calculated. And our system works like this. This is V2I system. So we had a DSRC unit. This is portable unit on the roadside. Portable means that wherever a work zone site is, you can take it there, or wherever accident happens, for example, and you have to close one lane or two lanes, you know, some lanes are closed, so congestion builds up. You can take it there, and what you need to do is basically to key in some parameters which are related to that work zone site or that accidental site location related. And once you do that, this is all set up. And of course, you have to have the vehicles carrying the DSRC units. And vehicles don't have to do anything. Drivers don't have to input anything. When this is present, if the software is running in it, this will engage them to acquire travel time. And then, of course, it will be periodically, in parallel, it will be periodically communicating that travel time as well as the start of congestion parameter back to the drivers. The way it works is that how this engages, how DSRC roadside unit engages the vehicles is that, you know, suppose if this is the work zone scenario, and then this lane is closed, and you can see this start of congestion, you know, congestion can build up, and this is the start of congestion location. And what we do is, this is again automatically determined the desired area. Depending upon where is the start of congestion location, it automatically moves that desired area according to that, just well before it, so that the vehicles can be engaged. So it sends the invite messages. You know, there are standardized messages which DSRC units can exchange. We are sticking to those standards. We are just calling this invite message because they are related to this particular application. So it will send an invite message, and automatically these vehicles which are in the desired area will receive that. All the vehicles will receive that, but they won't really take advantage of those. These vehicles will use that, and they will understand that they are in the desired area because the invite message will contain the coordinate of the desired area. So once they are in the desired area, they'll respond back with the accept message, and then this will choose the vehicles depending upon a find location check, which why that is needed I'll talk about in the next slide or two. So once these vehicles are chosen, what will they do is they will keep on sending notify messages once they cross through the congestion area. And once this is crossed, it reaches end of congestion area or end of monitoring range or end of work zone range, because that is what we will assume it is known. The start of congestion can build up, but the end is known. So based upon that, this will be able to calculate the travel time and the start of congestion. And if the travel time increases beyond a certain threshold, this can engage more than one vehicle at the same time. For example, if the travel time is half an hour, then you don't want to wait half an hour to update the travel time. So you can actually pick another vehicle. So at one time it can have two vehicles sending this roadside unit and notify messages. And just as a side, I also wanted to mention about the GPS accuracy kind of characterization which we did, because of course we are using GPS. GPS is considered now for granted technology. You know, DSRC is where our pitch is, but GPS is there for location detection. So what we did was we did some characterization in terms of actual location. So you can see that this is a big circle, right? If you take GPS reading for the same location, for the same physical location, it can give you different values. So we did it many times, and then the farthest location you can add a circle. So basically this radius, you know, this diameter becomes the inaccuracy of the GPS. So we did that, and you can see that the accuracy is about between 3 and 4 meter, or 4 meter you can say, with 90% confidence. And similarly, depending upon how big the position accuracy is, the distance accuracy can be affected as well, right? So each point could be here, here, or here, and then this point could be here, here, and here. So you can see the distance accuracy can be affected as well. So we did that in urban area. That was about plus minus 3 meter, but in rural area it was plus minus 2 meter. And this was really because of the interference problem. This is the regular GPS which you can buy. There are GPS, there are algorithms which you can use to make it highly accurate, or I think in few centimeters also. But we did not require centimeter accuracy for the scope of work which we were doing. So we were okay with this kind of accuracy. We also needed the direction accuracy, because we wanted to at least eliminate those vehicles which are traveling in the opposite direction. So that was, we had a huge margin, 180 degree. So, but again, we characterized this way that, you know, if of course if the 2 points are close enough, then the direction accuracy could be large, inaccuracy could be larger. Otherwise, if the 2 points are far enough, the direction accuracy could be very good. So you can see 5 meter apart, 10 meter apart, 15 meter apart, 10 degrees. We wanted to do that because we want to make sure while the vehicle is traveling, it can calculate its direction, right? So we want to get an idea of the direction accuracy. And why this? Because even at high speed, if you want to do it, say, every second or so, you can have about in the meter range. So if there are 2 points, if the vehicle is driving in the meter range, what is the direction accuracy? That's what we wanted to do. So this was, again, this was good enough for our work, more than good enough for our work. Again, so this is the kind of design. This is the desired area when the vehicle is coming. Again, invite and then accept, right, and then chosen and then notify, right? But basically, if you choose a vehicle in this area, and you know now the accuracy is in meters, few meters, and what happens is that once this vehicle sends back the where is my DSRC unit here? So I think I'm not showing the DSRC unit, but basically this is the zoomed out version. So desired area is in these circles. Now we usually have 3 coordinates to figure out to characterize the desired area. So if the vehicle is in this or this big circle, this will consider itself in the desired area, and it will respond with the accept message. Now this RSU, this RSU will basically determine if this vehicle is actually on the right lanes or not. It could be, for example, you can see there's another parallel road. It could be right here, and it could respond back with the accept message. But RSU does not want to pick this vehicle. So this is why RSU does a fine location check based upon this road parameters, that it is actually on these 2 lanes. So we did these checks could have been done within this vehicle, but we want to distribute the processing time so that it's not kind of, it doesn't really keep on waiting for the response that the vehicle is there. Plus, if there are many, you know, you have to do the fine checking. There are many circles you have to have, many coordinates you have to send, and then it may take longer for the processing of the vehicle. So it's the way we did was the coarse location check and then the fine location check. It distributed the processing time, and that was actually quite efficient the way we have been doing, and it's kind of seamless. It doesn't really it happens in milliseconds, and nobody really notices that. And after that, I just want to mention these. When I mention about the portable, these are the parameters which you have to set in the roadside unit, and it will be all ready for operation for that particular site. For example, the nominal speed limit, road direction, and end of congestion location, which is supposed to be known. This is start of monitoring range. This is the desired area parameter, basically road width and the road name and descriptive direction. Actually, this is needed because when it sends back the travel time and the start of congestion location, it sends a descriptive name of the road as well as the direction. For example, Rice Lake Road going towards airport. So that, because when the message is sent broadcast, every vehicle will be getting it. So, but it is not intended for every vehicle. It is intended for only those vehicles which are going on that particular road and in that direction. So that is why, to filter that out, we needed this. Otherwise, it will be very complicated just to make sure that only those drivers use it which are going in the right road. That will basically add some extra processing, a lot of extra processing on that. We did not do that. Again, this section I think skip this. I already talked about that invite, accept, chosen, and then notify messages, and in parallel broadcast messages are being sent. So this was our demo site. If some of you have gone to Duluth and familiar with the Rice Lake Road, which also goes to airport, this is the site which we chose. Of course, we chose this site. You can see this is pretty flat. This was the reason in the beginning, because we were using V2I and we did not have really much range to cover. So this is our RSU unit, and you can see the start of monitoring range. This is the end of RSU monitoring range. We had it asymmetric. The reason was that when our test unit, which was OBU, was passing by, it passed by this way, and then when it reaches here, the back of the car, we had the DSRC unit on the dashboard of the car. So when it crossed this, the back of the car blocked the line of sight. So our range in this direction was even reduced further. But when it is coming towards RSU on the dashboard, it had a clear line of sight, so it had a very good range. So this was the reason we had to make it asymmetric. But if the antenna is outside, on the top of the roof, for example, and it has a clear line of sight in both sides, then it should not be a problem. This is the log of the data which we got. You can see that the start of congestion and end of congestion. This is the data which we get. This is versus time, speed versus time, and this is the speed versus distance. You can see there's about 200 meters of distance, and this is recorded and sent by OBU in terms of notify messages and recorded by RSU. And once this crosses the end of congestion, you can see that the RSU can estimate the start of congestion as well as the travel time. The estimation is based upon what we did was that you notice a sudden speed of reduction when you hit the start of congestion location. And based upon that, there's a threshold-based detection. And actually, that is very adaptive. Doesn't matter how much. Whatever the speed reduction is, even if there's a little bit of delta, we can figure that out. And then based upon that, we can calculate the travel time and the start of congestion. And end of congestion, we always assume that the vehicles will pick up speed right away. Right? Doesn't matter what is the reduction of the speed is, but they will pick up the speed right away. We did try different profiles. For example, the depth of the congestion could be varying, right? So we simulated these congestion scenarios by taking our test drive vehicle on the curbside, on the shoulder. And that road was long enough. It has a long, actually one of the reasons to select this road was also that the shoulder was long enough, so we could simulate this congestion without disturbing the other vehicles. So that's how we did different scenarios, and each time actually without changing our RSU unit. Every time we did many test rounds, and every time it was working smoothly. It was able to adapt the travel time and start of congestion location estimation correctly. So this is after having described this work and field demonstration. Let me now talk about the V2V assistance part, why we needed that. And you already noticed that the distances involved, right? The congestion coverage length is about 200 meters or so, which we could do with our limited range DSRC Savari units. We had only half a kilometer range of those units. So although with 1 kilometer with V2I system can do a little bit better. So so this system, you know, this is theoretical range, 1 kilometer and 1 kilometer. So technically we can do this, that 1 kilometer congestion coverage length can be covered, and then maximum broadcast length can be about a kilometer. So vehicles which are already about a kilometer from the start of congestion, it's not really that useful for them. So the real usefulness can come if it grows. Real usefulness can come if you can cover actually few kilometers of congestion length, and also maybe few tens of kilometers of the vehicles which are maybe few tens of kilometers, maybe 10 kilometers or 5 kilometers away from the congestion. If they are informed about the congestion ahead, they can do some alternative decisions. Otherwise, it won't be really helpful. So we wanted to extend this range, this congestion length range, as well as the broadcast range. And the way we did was, although in the standardized DSRC units, the V2V, this version of V2V, the hop-to-hop, is not really is not being standardized. But again, I would emphasize that what we are doing is this part, the V2V part, hop-to-hop, will be controlled by our application. We are still sticking to the standardized messages by the DSRC, but this hopping will be controlled fully by our application, just so that the message can be carried to the vehicles which are much, much farther away from the origin. So to do this, we need selective relay and directive relay. What do we really mean by selective relay and directive relay? If some of you is from computer science department, you will be probably familiar with that. That is what is needed in ad hoc networks. Also when computers communicate, network of computer really communicate in that fashion. So that is what we actually try to do, also an ad hoc network of the vehicles. So first, what is selective relay? For example, if this is RSU, this will transmit the message, and you can see the message will be received by all the vehicles which will come under its range. Assuming omnidirectional antenna, all the vehicles will get that message. And you can see if this is the road and this is the roadside, and you can see many vehicles will receive that. So what we really need to do is, we don't want all the vehicles to propagate this message to ahead. And then if this happens, then all the other vehicles which will receive the next message, they will propagate, and that will be a broadcast storm. That will not work at all. So what we really need to do is, we want to make sure that the message is carried away in minimum number of hops and more efficiently, in the most efficient way. So what we did was, we split the distance around this depending upon the range. Our range was about half a kilometer. So what we did was, we had a 100-meter band, 5 bands. 100 meter, 200 meter, 300 meter, and 400 and 500 meters. And each band basically will have a randomly selected delay time associated with it. And the randomly selected delay band, for example, for the farthest band, the wait time will be 0 to 5 milliseconds. The wait time of the second farthest band will be 5 to 10 milliseconds, and then 10 to 15 milliseconds, and so on. So the vehicles which are in this band, they will receive the message. There could be more than one vehicle within this band who will receive this message. They will wait. As soon as they receive the message, they will wait for a time which is randomly selected between 0 and 5 milliseconds. And the vehicle which will wait for the least amount of randomly selected time, they will transmit first. And once they transmit, the other vehicles will receive that transmission as a second hop, and they will cease to transmit who are already waiting. And for example, if not a single vehicle is present in this band, then this band will be able to take over, because they will be also waiting. Their wait time is a little bit longer. So that way, basically, the message will go on depending upon how many vehicles have DSRC units. This will happen in the least, in the least number of hops. So that is what I mean by selective relay. We also need directive relay. What do I mean by directive relay? So directive relay means that if this is the origin of the message, and then you want to make sure if this is the road, work zone road, and say this is the congestion area, you want to make sure this really message goes to at least this road, and you don't want, if this is a crossing road, you don't want message to really deviate away. For example, if you come here, then this message should go here and here and here using the selective relay, but also at the same time we don't want this message, it could reach here also. We don't want message to propagate in this area because it may not be as useful. You could do this way as well as that way. That is also possible. But you want to make sure at least the road which is concerned, the message propagates that way. So what we do is we have define an angular region so that the angular region really tries to cover the road which is of concern. And we noticed many roads in Twin Cities metropolitan area as well as in Duluth, and we looked at about 10 to 20 actually kilometers, so about 10 miles width, and we noticed that the angular region which is less than 10 degrees is good enough to cover that. So and that way basically we can make sure that this really goes. So once the message is received, it also checks whether this is within this rectangle, with this angular area or not. If this is not, for example, in this case, if the message comes here, this message will go to this as well as that. But this will not carry this forward because this is outside of the angular area. Similarly, there is another thing regarding the directive relay, that suppose if this is another crossing road, and this is also within the angular area, but it will take the message to that direction. We don't want this to happen. But what happens is that we also try to carry the reference angle check. There is a curvature of the road involved, right? So we are assuming that the road curvature doesn't really take a U-turn, for example. If it does take the right angle turn, that is a unique case we'll have to keep in mind. But usually the natural curvature of the road we can keep in mind, and we can check for example, if this message comes to this and then it goes to this as well as that. So this vehicle will compare this angle as compared to this angle. If there is a huge difference, it means this is not along the natural curvature of the road. But this will check this, it will compare this angle and this angle. They are comparable as compared to this, right? So you can see that we will trace the natural curvature of the road, and that's way we can propagate our message on that road much longer. So this is the directive relay. Now one thing remaining in this V2V assistance part, which is really the back and forth propagation. Neither in selective nor in directive relay I talked about the back and forth propagation. For example, let's look at this. This is the vehicle. Suppose if this receives a message from this vehicle, and this will transmit to that using it passes the directive relay checks as well as the selective relay checks. But now if this will propagate again message, suppose in that direction, but basically this message will come back to this as well, right? This has already passed that message here. So we want to make sure that if this passes message to this back and forth, if this happens, then the same message will keep on moving back and forth as well, right? So we don't want that to happen. And to avoid that, there is another check which we can do. We can also, not only the natural curvature we can trace, but also there is, for example, the focal point of the angular region or DSRC. They are fixed locations. So we can see if the message is coming from the vehicles to RSU, we can see the distance, for example, of this with this RSU as well as the next hop's vehicles should keep on decreasing. For example, if this vehicle will compare the distance, this D1 with D2, and based upon that, it will not repropagate the message which comes from this vehicle. Rather, it will only propagate the message which will come from the vehicle behind it. So this way we can actually avoid this the kind of broadcast storm. This is the term which is used in the computer ad hoc networks. So we can avoid that. Having said that, now I think yeah, this is I have just one slide. I just want to mention this problem which we noticed, and we try to have a solution of that as well. For example, we are talking about now many kilometers away from the start of congestion. Vehicles will get an idea what is the travel time ahead and what is the start of congestion. For example, say this is about 10 miles, right? And this vehicle will be able to calculate its distance to the start of congestion, which is say 10 miles. But you can see if the road is curvy, then the straight line distance is easy to calculate, but this curve, the actual distance may be a little bit more than, it will always be either same or more than the straight line distance. So that we want to figure out that what is the difference between the actual distance and the straight line distance. So what we did was we try to do the polynomial fit. Of course, the one solution is that if the vehicle has all the maps, if they have the maps, just like your GPS navigational unit, he has the map, it can actually tell you the exact distance. If it has the map, of course, that will require a lot of processing also on behalf of the DSRC unit. We did not want to burden the DSRC unit with that. So what we did was, instead of sending this, in addition to sending the start of congestion location, we sent some polynomial fit. We tried to have the polynomial fit on different roads and try to find out the second order polynomial was good enough to get us the better estimate of the distance. And we noticed, you can see that this is the deviation of the actual distance and the second order polynomial distance of many roads. You can see the deviation is within plus minus 250 meters. So this was really, if the distance we are talking about 10 kilometer, right? This was 10 kilometer, and this kind of deviation is not really that much. But if you are nearby, yes, the deviation could be large, and you'll have to really consider. But nearby, if you're nearby, the curvature is not going to affect that much, right? You might be able to even see from the quarter of a kilometer. No, this is not that much a distance. This was the problem, especially when you are quite far away from the start of the congestion location. So we had a solution to that as well. And now I'll just talk about the demo. I think I'll be done in next now less than 5 minutes, so that I have some time for questions too. We started 3:30, so I'm a little bit, maybe a couple of minutes over time, but hopefully we'll have some time for the questions. This is the field demo. This is our RSU unit. We actually installed on a roadside signpost. And this was our test unit again in the vehicle. That is what I was talking about. The back of the car blocked the line of sight when it was going away from the RSU, but if it was coming towards RSU, the line of sight was clear. And this was just the GPS unit. We had a USB-based GPS unit which we could connect with the Savari network. And so this is our scenario. You can see this is our RSU. Before we were working only in this range, but now, because we did this demonstration with the 5 units. We had only 5 DSRC units, and one of our unit is RSU, and the other 4 we used as OBU. Actually, only one unit was our test drive, and the other units were helping to propagate the message forward. And we want to make sure that a few vehicles were close by, 2 vehicles were close by, so we could check all those tests which we programmed in our units. And this is the data log again. We did this demonstration many times. We had RSU set there, and we drove our test drive many times, and each time having a different profile of the congestion. This is just one example which I'm giving you, and each time we were able to estimate the start of congestion and travel time. Again, you can see it's about I think we were able to do about a kilometer, which as compared to 200 meter only with V2I, with the 5 units, and from those 5 units, one was our RSU unit. But basically, as a proof of concept, this was good enough because it was scalable. If we have more DSRC units on the roads, we could scale it we don't have to do anything. Everything is ready. We have programmed it this way that this is scalable. It can actually carry the message forward or cover the congestion length, which is few kilometers long, and carry the message forward at least few tens of kilometers if the penetration of DSRC unit is present on the road. So that is what it needs. Otherwise, in the V2I part, what infrastructure part is needed is just one portable DSRC unit. So with that, I will, before I rest my case, I just want to mention a couple of observations. I think I already talked about that. It's a different traffic condition. It can automatically adapt. Basically, once you just program with the initial parameters, it can adapt to that. No, sorry. This is that point. This point is that if the traffic condition is changing, for example, in rush hour, congestion can build longer, and then it can after rush hours it can come back to normal. So this is automatically covered. This keeps on estimating congestion, start of congestion in real time. So in real time means every 15 minutes you can have a threshold. Every 15 minutes or even sometimes 5 minutes. Every 5 minutes, if you want to update, it can actually update that. So it is fully portable. All what you have to do is just set the parameters, and yeah, I think most of these things I talked about when I was describing the system, and I think that is my summary. This is exactly what I talked about, and now I think we have some time for questions, if there are any.
If you have any questions, you'll need to speak to the mic, and if you are online, there should be a box on your interface that you can type a question into.
I'll start. As I understand it from talking to the vehicle manufacturers, many of them already have Wi-Fi chips built into the latest model cars, and they're using them to update diagnostic software. I'm also told that these same Wi-Fi chips, whether they're following the 802.11 or 802.11ab, etc., could easily be adapted to the DSRC protocols, which are 802.11p. Do you feel, and they're sort of implying that the speed of deployment could be much faster than most people think, that it could be changed by simply upgrading the firmware?
Yeah, that's.
Do you disagree or agree with that?
Yeah, I think I'm not in a position. I don't know about this situation, but I think I was going to say before you already talked about firmware. I was going to say I don't know if they will be able to do it just with the firmware change. It actually may not be, because there are some speed limitation. You're using a different spectrum as well. So you might have to change some chips as well, and if that is the condition, there's no way you can adapt easily. They are putting Wi-Fi chips for some other purpose, but I would say that some of the application, for example, this application, it doesn't require that low latency which DSRC offers. Wi-Fi could do something like that. So some firmware, not even firmware, some software change can actually make this kind of system implementable for those vehicles, but those vehicles may not be able to adapt to the DSRC standards so easily. So some of the other applications which DSRC can offer, we may not be able to do with those. So I think this is what my take is. I don't really think it will be possible just with the firmware change.
But by the same token, simply using, let's say, your smartphones with Wi-Fi on board, there's just too much time associated with handshaking.
Absolutely.
For you to have vehicle-to-vehicle or even vehicle-to-infrastructure for this to work.
Because here it doesn't really matter that much, right? Here the low rate in terms of travel time acquisition, it doesn't really matter that much. So this is why I'm saying for this particular application, maybe a software change can make that work, but not for the other applications. For example, say the merge assistance, if somebody is talking about the collision avoidance kind of scenarios, they cannot be implemented with the Wi-Fi environment.
So the message you send back from the system to the drivers is the travel time.
And there are two things: travel time and the start of congestion location.
Okay. And when you say travel time, then it's a travel time of a particular vehicle which you tracked in terms of the actual travel time for that vehicle pass through.
That is true.
Okay. Okay. So that's essentially. Let's say the travel time is, if that particular vehicle's travel time is 20 minutes, then that's when the driver gets it, it's already 20 minutes late.
That is true. It is lagging 20 minets. But if this is why we are, if for example our threshold was about 15 minutes, if you are above 15 minutes, you can pick another vehicle too. So your two vehicles are at the same time you're tracking, and so you can. So for example, travel time is say half an hour. But you can update every 15 minutes because you have two vehicles on the road. You could pick 3 more. You can reduce the threshold. So this is a part of the program or the software which we have developed. You can choose whatever you want to that threshold. And I did not show you all the parameters. This is one of the parameters which you can program your RSU unit so that it can update every 5 minutes, for example. It will pick another vehicle every 5 minutes.
Boy, if nobody wants to ask questions, I have a whole lot. When you're talking about directional accuracy, that works very well if you're going at higher speeds. But at slow speeds, you know, you're reading GPS once a second. At once a second at slow speeds, you're not going to really know what the direction is going to be because it can randomly move back and forth.
Absolutely.
Is that not an issue?
Yeah. No, this was an issue, but I think in our case, what we wanted to do was to eliminate the vehicles which were traveling in opposite direction. So in this particular case, it was not the issue. Their issues can be solved in various ways that you don't have to. We were taking GPS reading every 1 second, but you don't have to use the previous reading. You can store the few previous readings, and you can use them to calculate the direction accuracy. We tried that as well. So I think this is just a simple fix. For our purpose, it's not a big deal.
Any other questions?
Yeah, I had a question about, and I realize this was just a demonstration, but I'm thinking about deployment. With your hopping scheme, it seemed that the car would have to have a priori knowledge of the scheme, or is that built in the DSRC message that they've thought of this application and all the information you need about the angles and the tolerances are in those messages?
Everything is in the RSU roadside unit. When you set it up, so I did not show you the additional parameters which we need for the V2V assistance part, so you will have to just send some parameters like focal point of the angular region, these kind of things. The vehicles don't need to do anything as long as they're running the software which we have developed. So as long as they're running that software, it will be transparent to them. So everything is sent to them through the RSU. So they will basically, for example, the angular region, you have to define that. The focal point will be sent by RSU to those. So they will have that to compare or do the calculations.
So the vehicle has to be aware of what that means and have programmed in their own onboard unit?
No,
or
the RSU will be sending all those parameters. For example, those time delays, RSU will be sending them.
Yeah, but I'm just wondering, in order to process that information, make meaning of it, so does the RSU or the onboard unit have to have your application?
Yes, they need to have that software running. Yeah. Absolutely. And that is what we developed the software for RSU as well as for the vehicle unit.
Okay, so to deploy this, that would have to be part of the standard application.
Yeah, it has to be standard application. It should be running parallel to, say, for example, many other applications which are running at DSRC unit. So this will automatically kick in when an RSU comes in. It will automatically kick in. So it will be running in the background. I think that is the vision, that once the DSRC units are in the vehicles, the many applications will be running in the background, will be dormant. But once they enter in the field, for example, the work zone area, they will become active. And if they want to use the collision avoidance application, if something like that happens, they will come in the foreground.
So it's almost like all the vehicles have to be in sync on what applications are supported.
No, there will be some standard applications which will be running in the background. So I think yes, absolutely. Driver doesn't have to say turn it on and off an application. It should be transparent to the driver.
Okay.
If there are no more questions, please join me in thanking Professor Hayee for his presentation.
Thank you very much.
2 weeks from now, we're going to have I'm trying to remember the speaker's name, but I'll be talking about bicycles and tracking bicycles, if I remember correctly. Right. Lauren Tervina will be talking. He's from the Department of Computer Science here at the university, and we'd like to have you all come back 2 weeks from now for that presentation. Thank you.